Is it on? Yeah. This is on. Okay. Right.
Yeah. Thanks. Okay, let's settle down and restart the morning session. It's my pleasure to introduce Reinhard Genzel, who's talking about mass angular momentum budgets and quenching in high-Z galaxies.
Thank you, Chris. And thank you, Joel and Avishai, for continuing the wonderful tradition, and I apologize that I haven't been here for the first day, so if I insult in any way, fashion, or manner those who have talked before me, I apologize deeply. Okay, so what I will do is to talk about two subjects we have been working on, and I promise you there's some new results. And the main topic is going to be Quemas 3D. So some of us Europeans have this little telescope down south. Not as large as yours, but you know, and we have a new instrument since a few years called Quemas, which is 24 symphonies in one. So we can actually look at, you know, considering that we have to look at the sky, typically 15 to 20 objects at any given time. So that's, of course, that multiplex advantage is fantastic. Now, it's not new to you using Mossfire, but of course, here we have the two-dimensional information, although, and that is a disadvantage without adaptive optics. So the Quemas 3D survey is based on a parent survey mass selected from 3D HST candles in redshift range 0.7 to 2.6. And our main survey has been about 600 mass selected surveys in 3 bands in this redshift range. Now compared to MOSDEF and other surveys, you see we have a few, not so many galaxies. And the main reason is, although we're only looking at one band, naming that one around H alpha, is because we're really integrating deep. So our integration times are, my MOSDEF is 2 hours. We integrate between 4 and 30 hours. And that, in fact, has brought about some substantial new information, I would say, which has not been possible before. In particular, high-quality spectra. The outflows come to mind, but also pushing now the survey down into the red sequence. We are seeing H alpha in the red sequence, one of the topics I will discuss today. So here you see stellar mass, star formation rate plane, and here's the main sequence line. The yellow and red objects were the 110 objects which we had before, Quemas in the symphony surveys. Some of them about a third in adaptive optics. And the Quemas survey is in dark blue in terms of the targets, and the ones which you have already observed are the slightly higher blue. In the color plot, you're seeing that whilst the UV selected symphony targets, often BXBM objects from UV rest frame spectroscopy, were biased towards bluish galaxies. With the 3D HST optical spectra, it's now possible to push into the entire sample of also reddish dust extincted star formers, as well as in terms of the quiescent galaxies. So the statistics at this point is around the main sequence. We are detecting about 90% of the objects we're looking at, and for most of them we spatially resolve. That is despite the fact that we are, seeing limited, and that's because at the depth we can push out into the outer parts of the halo, and that will become very, very important in a few minutes. Down below, we see 20% of the objects. 20% of the objects, which are, formally speaking, dead, have detectable H-alpha, and in fact, half of those, again, are spatially resolved, and you'll see what we are learning from that. So now, as you've seen that kind of a diagram before for me, so I won't dwell on it, that's the velocity fields in H-alpha of only 200 galaxies. We're not now anymore in the limit of trying to impress people with ever more objects in here. We're now in the limit of not cluttering up the field. So I could show you several of those. And in fact, there is a simultaneous Redshift 1 survey cross by our colleagues in the UK, which also produces these kind of things. So, by now we have certainly close to 1,000 of these types of diagrams, and they all look pretty much like this. And we can debate, of course, whether these regular velocity fields, which are the norm, in every single case really do mean it's rotation, or whether it's orbital motion where you have perhaps a merger, etc. But I would say the verdict between different groups doing this, including in fact now Muse entering the field as well at slightly lower redshift, another instrument on the VLT. This paper here by Contini et al. So between the three surveys going on, I think the numbers you're getting to here is that 70% of those high redshift star-forming galaxies are rotationally supported but highly turbulent disks. Never mind, there can be and will be interlopers. That's very, very clear. And not in every single case can you be sure that rotation is the dominant case. Now, these surveys have typically emphasized stellar masses greater than 10 to the 10, although we are now beginning to push down to below, where we know we're entering the so-called dispersion-dominated galaxy regime, and we know that's a much more tricky thing in terms of what the dynamics is like. Now, with all these spectra and the ancillary wonderful HST information, we can therefore, for these galaxies, go ahead and model them. And in fact, similar work is being done by Sedona Price and others on MOSDEF, where you basically combine the HST imagery and then the two-dimensional velocity information in H-alpha to derive from that, as a first-order estimate, the dynamical mass of the galaxy within the size of the galaxy, within RE of the HST. And there are various ways of doing this. Now, in fact, in more detail, this turns out to be fairly tricky, because once you start making a quantitative analysis, not only do you have to correct for the fact that you don't have the resolution to see the inner parts of the galaxies, there is the question whether you can assume for all of them that they are exponential disks, although that seems to be reasonably well justified for all but the most massive galaxies in the HST imagery, and corrections to deviations from n=1 can become important. Cutting this short, there's a paper now out by Andreas Burkhardt. You see, we're working with a theorist doing observations. Andy has become a throughout observational astronomer. And in this paper, we've derived for 400 galaxies in this redshift range the angular momentum distribution. There's 2 points. Point number 1 is the distribution in terms of lambda parameter. In terms of lambda parameter, is consistent with the lambda parameter of the dark matter. And in fact, also its logarithmic width of about 0.25 dex. So that's consistent. Or turning it the other way around, if you assume for each and every one a lambda of 0.035, which of course is wrong, right? You will have a distribution around that. Then we can deduce the ratio of the baryonic, the disk angular momentum, to that of the dark matter, and that's plotted here as a function of log m. And compare it, for instance, to redshift 0, here from the work of Fall and Romanowski, for disks, these red objects, where basically they are around 0, meaning that the dark matter and the baryons approximately have the same specific angular momentum. And the same is true for our high redshift sample if you look at the rotationally dominated objects. If you look at the dispersion-dominated objects that, you're no surprise, you find that they are lower in this diagram. They're also lower in mass, and that is an interesting domain which I don't have time today to discuss. The main point here is, on average, the angular momentum of those galaxies indeed is what you would expect from the dark matter distribution. And that is not entirely trivial, as we know from Avishai's, Danovich et al. Work, because you can start off with some angular momentum, then you can lose it, you can gain some, supernova feedback comes in, and so forth. There's a lot of coming and going and taking and producing, and so in the end, it's a bit of a magic. Now, the illustrious simulation results are more or less consistent, although they still have the old disease of having a little too little angular momentum, okay? But the effect is not huge anymore. Let's go to the mass budgets. Okay, so you have now a dynamical mass at RE, or you can extrapolate this to total. Then you have a stellar mass from HST analysis, SAD modeling, as everyone does. HST sizes, so you know what the size distribution is. And then you have to take into account the gas. Now, the molecular gas you can get from the scaling relations, which are now pretty solidly established. The general belief is that H1 within RE at high redshift is a small correction. In fact, it's partly covered already in the metallistic corrections we are putting into these scaling relations. But H1, formally speaking, is not in. Therefore, these gas masses are a lower limit to the masses. So then you can compare, and that's done here, the baryonic mass fractions of the entire galaxy as a function of redshift. So the Quemas 3D survey is here are the mean values, the 68 percentile deviations, and you see here's all the distributions. So there is a wide range, and in fact there are some which are way into the unphysical limit. And we've been really scratching our heads over that, and in part that's because of error bars. In part, it could be due to the fact that, as is described in this paper here, there is a correlation between baryonic fractions or stellar fractions and surface densities, such that, at least for the gas masses, we have to worry whether, our scaling relationships, which are so far integrated scaling relationships, have a surface density part to them, which would diminish the gas fraction sum at the highest densities. So that's a worry, especially at redshift 2, but not so much at redshift 1. Now you see the overall picture is that, about 30-40% of the total dynamical mass on the galaxy scale are baryons, so there is certainly space left for dark matter. However, at redshift 2, they're getting awfully close. They're getting awfully close, and I'll spin that theme for you a little further in the next slides. And I think, Sedona will give you more discussion on what she finds on MUSTEF, but I think generally the two results agree pretty well. As far as the theory is concerned, the various modeling is shown here in red, green, and blue, agree at the lower redshift, but you see here there is a discrepancy which, as you well know, exists since some time. Gas fractions and star formation rates at redshift 2, as observed, are higher than what comes out of almost everyone's theoretical model, or should I say, out of everyone's theoretical model. So there is that tension again. Now, an interesting point, which I'll also come into a little more, is that these very high baryonic fractions, we think, are mirroring those in early type passive galaxies at redshift 0. Now, this work we're doing is so deep now that we can actually try to push the rotation curves beyond RE. So that's the next part of the talk. We do this both in individual galaxies. We have at this point about a half a dozen galaxies where we've integrated the data to, about 10 to 30 hours individually. Here's one of them where you see the H alpha distribution. On the HST imagery here, the velocity field on the HST imagery, then the cut along the major axis in what you would call the projected rotation curve, and then over here, the velocity dispersion field and the cut along the major axis. So again, with this, you can then derive individual rotation curves, as I said, into what you would call the outer halo, into the outer disk region, inner halo, for about 5 or so galaxies, but we can also do stacking. That's a fairly tricky procedure. I don't have time here to discuss this. This is in a paper which Philip Lang, student, has produced, which will come out pretty soon. So what is the result? Well, the result is pretty clear and pretty surprising. Okay, so here in units of R1/2, or RE, you see the effective rotation curves. So the inner part, of course, is still affected by beam smearing, so don't take that literally, but you see there's clearly a peak, and then they're not flat. Rotation curves are not flat. Now, in the 5 individual cases, you could argue, well, we chose them, and we did deliberately, and integrated away, and proved that this factor is true. But here the stacks, okay? The stacks in this paper by Lang et al. Cannot be caused by pre-selection, and so they are also falling. So the rotation curves seem to be falling. And they seem to be falling more at redshift 2 than at redshift 1, so there's a dependence on V over sigma. Okay? So rotation curves seem to be falling. So if I combine this here into a single rotation curve, let's call that, at least preliminarily, that's our high redshift rotation curve of a massive galaxy. Well, that is actually not too badly fit by a good old Freeman disk. Okay? Now, a Freeman disk doesn't have dark matter. And here we are at 2 to 4 scale lengths. Now, wait a second. Where's the dark matter? Now, let's be careful. Let's be careful. These are not Freeman disks because we have turbulence. And as Andy has pointed out, and many others know, that means you have a pressure term, a radial pressure term, due to the random motions, such that the effective rotation velocity is the circular velocity squared minus this term here, which increases if sigma naught is constant. Now, sigma naught in, say, this case, you can measure, is constant. Okay? So in the cases where in the individual rotation curves, we do see that the sigma naught stones become smaller. So that by itself is very interesting, because what causes the sigma naught out there, where the star formation rate already is fairly low.